Okay, welcome. Today we're going to start talking about the structure of the atom. Now, the atom is not really the tiniest piece of matter, but it is what all kind of matter that we see around us is made up of. And atoms were the first structures in the universe after the Big Bang. So, atoms are made up of some particles, and they come in three varieties. We have particles called protons and electrons. In a moment, we'll talk about these particles called neutrons. Now, atoms are the same name as the elements in the periodic table, which you're familiar with. The first element, and the most common element in the universe, is hydrogen. That's what the H stands for. Hydrogen has one proton and one electron. The proton is in the center. We call that the nucleus. But unlike the nucleus of a cell, there's no boundary or barrier here. The proton just sits in the middle, and orbiting around it, which is what these dashed lines mean, is the electron. Now, these symbols here, plus and minus, are important. The proton has a property we call charge. Somewhere along the line, maybe fourth grade, middle school, you learned that there are positively charged things and negatively charged. Okay? And you also learned that negative and positive charges attract, and that like charges, meaning negative and negative, or positive and positive, repel. So the simplest atom, 95% of the universe, is hydrogen. Now you might be wondering, how come, if I learned in middle school that opposite charges attract, the electron doesn't fall into the proton? Now, since it's orbiting, you might think, okay, it at least would spiral in like a decaying satellite. That's a wonderful question. And the answer to that leads to a different branch of chemistry and physics we call quantum mechanics. But the fellow who taught us about that was Niels Bohr. And I call him the Great Dane because he was Danish. And he taught us something special about atoms, that because of what we now know is called quantum physics or quantum mechanics, the electron orbiting the proton is stable. It stays like that forever. That's pretty cool, all right? Now, helium is the next most prevalent element, and it's made up of two protons, both positively charged, and two electrons orbiting. You might ask, why don't the electrons collide? Again, we get to cheat for the moment and say quantum mechanics. But there are these two new entities called neutrons. This zero means that they are neutral. They have no charge. Now, fun fact, hydrogen is the only element with just a proton and a neutron. Starting with helium and all the other elements in the universe, some 116 or whatever, they all have neutrons. Now, the topic for today is what in the structure of the atom is so special about having neutrons. Why neutrons? The cool thing is we don't have to do atomic physics to use logic to figure this out. So go back to hydrogen, no neutrons. Now, scientists knew that there were neutrons a century ago in helium, but they didn't know why they were there. Later, fancy experiments were done with atom smashers to find out all about the neutrons. But I want to show you today that with just logic and critical thinking and some basic science, you can deduce what the neutrons are all about. So let's look at the helium nucleus. It has these two protons. And again, somewhere in your early science classes, you learned that like charges repel. So you might be wondering, how does the atom stay together? At least the helium atom. It has these two positive charges, and they should repel. And the atoms would all blow up, and we wouldn't be here, and I wouldn't be giving this lecture. Now, we might guess that the neutrons have something to do with that. The question is, how? You might think, oh, well, the neutrons have mass, and they kind of hold the protons together. Not a bad idea, but it turns out that gravity is very weak force. In fact, the strongest force in the universe is electricity and magnetism. That's the strongest force. The next strongest force in the universe is gravity, but it's still very, very weak. It's actually not the second strongest. It's the second strongest of the ones we're going to talk about. Gravity is so weak that the mass of the neutrons is tiny. It can't be gravity. Now, the question is, why do we need the neutrons at all? Again, to keep the protons from flying apart, and it can't be from gravity. It turns out there's another force. In fact, another time we'll talk about there are 4 fundamental forces in the universe: electromagnetism, gravity, and 2 others that both operate only inside the nucleus of the atom. And they have very unfancy names of strong nuclear force and weak nuclear force. The neutrons, it turns out, are able to keep the protons together by a new kind of force called the strong force. Now, you would think we just made that up, right? Well, later on, scientists were able to use atom smashers to break apart neutrons and protons. They are not elementary particles. The electron, amazingly, is what we call elementary. There's nothing inside of it. But inside of protons and neutrons are tiny little particles that we think are elementary, meaning the simplest, and they are known as quarks. And scientists later on got all the details about what's going on with the quarks, but I promised you we could figure this out basically on our own, and there it is. Protons want to repel. They don't really have emotions, but they will tend to repel. They're like charges. Whatever the neutrons are doing, it can't be gravity, and they are neutrally charged, so it can't be electricity. They must be doing something to hold the protons together. Now, if you think about it, even if they're holding the protons together, that electric force is very strong. As we go up the periodic table and we load more and more protons into each atom, the protons are under incredible tension. Turns out nature has to put in more and more neutrons just to keep those protons from flying apart. At some point, no matter how many neutrons we put in elements above something like 85 or 90 in the periodic table, nature cannot put in enough neutrons to keep the atoms together, and they decay. That's called radioactive decay. And if you get bunches of those atoms and stick them together and they decay, you get an atomic explosion. And that's what this fellow taught us 100 years ago, that the energy inside an atom released when the protons fly apart is enormous. And we all know how much energy that is if we were paying attention earlier in school. E equals mc squared. So it's amazing to think about, just looking at the basic structure of an atom, that the protons want to fly apart. The neutrons logically must be there. How do we know that must be why the neutrons? Because hydrogen doesn't have any. So the neutrons must be how protons are being held together, but that doesn't erase the repulsive force. So we have to put more and more neutrons in. Eventually atoms become unstable, and that's how we get nuclear radiation, and ultimately something perhaps catastrophic like an atomic bomb, or something useful like a nuclear reactor. And there we are.